Los Angeles, California. The second largest city in the nation, the greater Los Angeles area is home to a whopping 18.3 million people and sees an average of 50 million tourists per year. The entertainment capital of the world, the city is world-renowned for Hollywood, the movie industry, and its abundance of celebrities. Not only is it famous for entertainment, Los Angeles is also one of the most diverse cities in the world, home to sizable populations of people from pretty much every country on the planet. Revered for its mild climate, beautiful sunsets, and intriguing mountains, Tinseltown sure is a snowbird's paradise. If you're the inquisitive type, your mind may wander as you drive through the city and look around. How the heck did these mountains around town form? How about the valley that LA's in? Everyone knows about the San Andreas Fault, but what's the science behind it? When's the big one gonna hit? Why is LA so dang rich in oil? If you've had any of these questions before, you're in luck. Why? Because we're going to answer all of them and more in today's episode of Solomon's Outdoor Adventures, as we discuss the geology of Los Angeles. Let's start by going way back. I'm talking 1.7 billion years ago, when the first chapter of La La Land was written in the rocks. The oldest rocks that outcrop around Los Angeles are 1.7 billion year old metamorphic rocks that are found in the San Gabriel Mountains north of town. These rocks are mainly gneiss, schist, and amphibolite in a unit known as the Baldwin Gneiss. This unit is a part of the Mojave Crustal Province, a group of very old rocks that comprise the westernmost edge of the core of the ancient North American craton. A craton is just a fancy term for the main core of a continent. Anyways, these rocks in the San Gabriels shed light on what the area was like back in the proverbial day, and the Baldwin Gneiss in particular represents the core of a very ancient volcanic arc on the western edge of ancient North America. It is hypothesized that the arc was active from about 1.8 to 1.6 billion years ago, as the dates obtained via uranium-lead dating of the rocks yield those ages. For the next 1.4 billion years, what would become Los Angeles was actually pretty boring. You see, from just after the time of the emplacement of the aforementioned Baldwin Gneiss until about 250 million years ago during the Mesozoic era, the entirety of Southern California was under a shallow sea. Rifting occurred during the late Proterozoic eon, plunging the area underneath the ocean and transforming it to a passive margin. A passive margin is a transition zone between oceanic and continental crust in the absence of a plate boundary, much like the Atlantic coast of the US today. Sedimentary rocks such as limestone, dolostone, shale, mudstone, and sandstone were deposited during the Neoproterozoic and Paleozoic eras, when the area was a shallow sea. This all changed during the Triassic period when the Farallon Nation attacked. From about 250 to 50 million years ago, the entirety of the west coast of North America was an active subduction zone, the Farallon Plate plunging beneath the North American Plate. A subduction zone is a type of plate boundary where two tectonic plates are converging into each other, and the denser plate dives, or subducts, beneath the lighter one. This tectonic regime was responsible for building the massive Sierra Nevada batholith. The Sierra Nevada is chiefly composed of rock that is derived from the ancient core of a volcanic arc that was generated by this subduction zone. To learn more about the geology of the Sierra Nevada, click on this video. Southern California was not spared by this subductive tectonic regime. The ancient Farallon subduction zone was responsible for effing up the sedimentary rock that was deposited during the Paleozoic when the area was a passive margin. These sedimentary units were highly metamorphosed, becoming marble, schist, gneiss, quartzite, myelinite, and hornfells. Units such as the Pelona Schist and metamorphic suite of Big Dalton Canyon, which are found in the San Gabriel Mountains, are representative of these processes. These high-grade metamorphic units are home to some pretty cool gemstone deposits, including a corundum and lapis lazuli occurrence in the San Gabriel Mountains. To learn more about the geology of these gemstone deposits, click on this video. In addition to metamorphism, granite and granodiorite plutons were widely emplaced throughout the San Gabriel, San Bernardino, and San Jacinto Mountains, as well as throughout other ranges in Southern California. Plutons are masses of igneous rock derived from magma that cooled slowly below the surface of the Earth. These granites and granodiorites are chiefly Triassic to early Paleogene in age, dating back 250 to 50 million years, and attribute their genesis to the processes involved with the ancient subduction of the Farallon Plate beneath North America. From the end of the Cretaceous period 66 million years ago to today, the vast majority of rocks that have been deposited in the Los Angeles area have been sedimentary rocks, of both marine and non-marine origin. The oldest of these units are late Cretaceous sandstones and conglomerates in the Santa Monica Mountains, but the vast majority of the sedimentary units around LA are marine sandstones and shales that date back to the Miocene epoch, roughly 23 to 5 million years ago. These units represent a time when the area was under the ocean, in both shallow and deep water environments. The Topanga Formation in the Santa Monica Mountains is perhaps the most ubiquitous of these Miocene sedimentary units. The youngest of LA's rocks includes sedimentary units from the Pleistocene epoch, dating back 1.6 million to 11,700 years ago. These include coastal floodplain, alluvial fan, and uplifted marine deposits. Throughout the Pleistocene, sea level fluctuated due to the changing climate of the Earth, and this is recorded in the sequences of marine, non-marine sedimentary units. The youngest deposits in Los Angeles are Holocene alluvial fans and stream channels of the Los Angeles and San Gabriel rivers. Sedimentary units are widely found in the Santa Monica Mountains, Palos Verdes Hills, Baldwin Hills, Puente Hills, Chino Hills, Simi Hills, Santa Susana Mountains, San Fernando Valley, and Los Angeles Basin. The San Andreas Fault is ubiquitous amongst Californians and non-Californians alike, but did you know that the greater Los Angeles area is home to over 100 active faults not named the San Andreas Fault? These faults all pose serious seismic risk to the 18.3 million residents in the region, and they shed light on the complex geology going on underfoot in LA. Perhaps surprisingly, the city of Los Angeles is not located on the San Andreas Fault or the North American Plate. It's actually on the Pacific Plate. The San Andreas Fault, which denotes the boundary of the two aforementioned tectonic plates, runs north-northeast of the city on the other side of the San Gabriel Mountains. Despite this, Los Angeles is located in a highly seismic zone of interconnected faults, as the plate boundary is not a simple one-fault border. It's really a transition zone with hundreds of faults running through it. Some notable faults that run through Los Angeles include, but are not limited to, the Hollywood, Palos Verdes, Newport Inglewood, Puente Hills, Elsinore, Raymond, Compton, Northridge Hills, and Sierra Madre faults. These faults are all extremely young, geologically speaking at least, having formed within the last 5 million years or so. The current tectonic regime in the area was not in charge until only 30 million years ago, when the San Andreas Fault overthrew the ancient Farallon subduction zone. At this time, the first portion of the Farallon Plate fully subducted below North America. This marked the first contact of the Pacific and North American plates, and while the Farallon Plate was moving towards the North American Plate during its reign, the Pacific Plate is different in that it laterally slides past the North American Plate rather than converging into it. The Pacific Plate moves north-northwest, while the North American Plate moves south-southwest. As such, the Pacific-North American boundary forms a transform plate boundary exemplified by strike-slip faults rather than a convergent plate boundary with a subduction zone. As with all things in life though, it's not that simple. Why? Because the San Gabriel Mountains, Santa Monica Mountains, and other mountains in the transverse ranges near Los Angeles are being actively uplifted by thrust faults associated with the Pacific-North American plate boundary, despite it being a strike-slip dominant transform plate boundary. This occurs because of a big bend in the San Andreas Fault. The San Andreas Fault runs from Bombay Beach at the Salton Sea in the south, northwest for 750 miles to Cape Mendocino in Northern California, where it ends at the Mendocino Triple Junction and the Cascadia Subduction Zone picks up north of it. En route to the Mendocino Triple Junction, however, it takes a sharp bend west from Palm Springs to Carrizo Plain National Monument. Though the San Andreas Fault bends, forming an east-west trending section of it, the Pacific Plate continues to move northwards. As the Pacific Plate moves north and comes into contact with the east-west portion of the San Andreas Fault, all of the material on the Pacific Plate begins to crumple up and uplift, as it is no longer seamlessly sliding past North America. This process generates thrust faults and is actively building the San Gabriel Mountains and other ranges in the transverse ranges. This mountain building event is known as the Pasadena orogeny, and it's been transpiring for the last 6 million years and counting. In fact, the San Gabriel Mountains have some of the highest rates of uplift in the world. This exact tectonic process was responsible for the 1994 Northridge earthquake, which clocked in at a 6.7 on the moment magnitude scale. This earthquake occurred on a blind thrust associated with the Sierra Madre Fault, a fault zone responsible for uplifting the San Gabriel Mountains. The San Gabriel Mountains instantaneously rose 2 feet during the Northridge earthquake, and a blind thrust is just a thrust fault that does not surface, hence the blind terminology. It's no secret that Los Angeles is located in a lowland surrounded by mountains and hills, but what is the geologic origin of this valley? Let's discuss that now. The basin that the city is located in is aptly called the Los Angeles Basin, and it's the westernmost of 3 basins that share a very similar geologic history: the San Gabriel Valley to the east and the Pomona Valley even further east. In addition to the mountains that we just discussed, the LA Basin regales the regional tectonic processes that shaped Southern California within the last 30 million years beautifully. It is widely inferred that the Los Angeles Basin is Miocene in age, having formed roughly 17.4 million years ago. It's considered a pull-apart basin, opened up by the passing of the Farallon Pacific North American Triple Junction beneath Southern California. This triple junction was the precursor to the modern-day Mendocino Triple Junction, and throughout the last 30 million years as the San Andreas Fault has expanded, this triple junction has moved north. The triple junction passed through SoCal roughly 20 to 30 million years ago, and is the root cause of pretty much all of Los Angeles' modern topography. When the triple junction passed through the area, it generated crustal extension. This east-west rifting vertically rotated huge blocks of crust almost 90 degrees, opening up the Los Angeles Basin. The rotated blocks of crust would become the transverse ranges, while the void that the vertical rotation of crust left would fill with over 30,000 feet of sediments and become the Los Angeles Basin, San Gabriel Valley, and Pomona Valley. As aforementioned, the San Gabriel Mountains are still being actively uplifted today as the Pacific Plate moves northward. This means that the Los Angeles Basin is actively shrinking, as the area is experiencing compression. In addition to compression, the Los Angeles Basin is actively being cut up by right lateral strike-slip faults associated with the San Andreas Fault, double plowing the area. This tectonic activity has led to the formation of the over 100 faults that run through the area, and according to the USGS, there is a 60% chance that an earthquake of magnitude 6.7 or greater will strike Los Angeles within the next 30 years. It's no secret that Los Angeles is earthquake country, and everyone hears about the infamous Big One. While the San Andreas Fault doesn't run directly through town, it's close enough, and when the San Andreas does rip, it would be highly damaging to Los Angeles. We just discussed the regional tectonics at play here, and the over 100 active faults in the area, so let's take this time to discuss some past earthquakes that hit LA and the outlook of future earthquakes here. Los Angeles is traditionally home to a bevy of different Native American tribes, including the Tongva and Chumash people, and they have their own accounts and creation myths regarding earthquakes. The area was first settled by Europeans in 1771 when Mission San Gabriel Archangel was built by the Spanish. This was when written record keeping of earthquakes began, and within the 250 years of written record keeping in the area, 38 notable earthquakes of magnitude 6.0 or greater have occurred within 150 miles of Los Angeles, most recently the 2019 magnitude 7.1 Ridgecrest earthquake, which I personally felt quite strongly. Given this data, the average recurrence interval for a magnitude 6 plus earthquake within 150 miles of LA is 5.9 years. This means that a magnitude 6 plus earthquake strikes within this area every 5.9 years on average. That's pretty crazy, dude. It's been just about 5.9 years since the 2019 Ridgecrest earthquake, so we should be gearing up for a 6 plus here pretty soon if we're going off of averages. Of course, averages don't work like that, but it's interesting to run the numbers. The largest possible earthquake that could strike the greater Los Angeles area is a magnitude 8.3, which would mark a full rupture on the San Andreas Fault. The more likely scenario would be a magnitude 7.8 earthquake to rupture the southern section of the fault, which, according to the USGS, would likely lead to about 1,800 casualties in the greater Los Angeles area. I personally think that this estimate is a little conservative, but I'm not a disaster planner. I'm just a geologist with a YouTube channel. Despite this, the city is built to strict seismic code, so the majority of buildings in LA would not collapse, even in a powerful 7.8. Highways such as I-10, I-5, and I-15 would be destroyed where they cross the San Andreas Fault, and rail lines would also be severed. Fires would likely erupt due to the earthquake as well, as power lines and gas lines would be heavily damaged. This would be where most of the casualties would occur in the event of this earthquake, after the shaking was done. Los Angeles would also experience liquefaction, and it would likely take months for enough aerial aid to arrive for 18.3 million people. The USGS postulates a 31% chance of a magnitude 7.5 or greater earthquake to strike Los Angeles within the next 30 years. Of the major faults in Los Angeles itself, the Hollywood Fault could produce a magnitude 7.0 earthquake, the Palos Verdes could produce a whopping 7.8, the Newport Inglewood could produce a 7.4, the Puente Hills Blind Thrust could let a 7.5 rip, the Elsinore could produce a 7.7, the Raymond could produce a 7.0, the Compton could let a 7.4 rip, the Northridge Hills could produce a 7.5, and the Sierra Madre Fault could produce a magnitude 7.7 earthquake. A magnitude 7 plus rupture of any of these aforementioned faults would likely be more deadly to Los Angeles than a comparable rupture of the southern San Andreas, due to the fact that these faults run right under LA rather than being separated from the city by a large mountain range. The Palos Verdes, Elsinore, and Sierra Madre faults would be especially dangerous due to their large potential magnitudes in the event of a full rip. A full rip of the Puente Hills Blind Thrust would likely be the most dangerous event, given its attitude as a thrust fault, the fact that it runs almost directly beneath downtown Los Angeles, and its potential of a magnitude 7.5 earthquake. The USGS estimates over $252 billion in damages, hundreds of thousands of people displaced, and up to 18,000 casualties in the event of a Puente Hills full rip. This Puente Hills USGS estimate has 10 times the casualties as their San Andreas estimate, so that should show you the magnitude, pun intended, of this possible disaster. If you want to learn more about the prospect of the big one hitting LA and of California's fault lines in general, click on this video. This 30-minute deep dive on California's earthquakes and fault lines covers it all, including past earthquakes, California's earthquake geology, and the outlooks of the big one hitting Southern California. Having existed in its modern form for the last 17.4 million years, the Los Angeles basin has spent much of its time underneath the ocean, in both shallow and deep marine environments. As such, many marine organisms have lived and died here, their remains falling to the seabed as they perished. The Los Angeles basin has been tectonically active for its entire existence, with faults cutting it up and building mountain ranges like the San Gabriel Mountains. With such fast rates of uplift, these mountains have rates of erosion that are equally as fast. As such, sediments are quick to accumulate and bury sedimentary layers rich with marine organism remains. As these marine organism remains get buried so quickly, they are subjected to high temperatures and pressures, buried by as much as 30,000 feet of sediments. These temperatures and pressures at depth are sufficient to transform their remains into oil and natural gas. Rinse and repeat this for 17 million years, and you get the richest basin in the world in terms of hydrocarbons per volume of sedimentary fill. The high rate of regional erosion is not the only factor that favors oil deposition in the Los Angeles basin. Two other key aspects combine to form the perfect storm of black gold in the City of Angels. First, the Los Angeles basin is incredibly rich with very well saturated oil sands. Oil sands are a specific type of sediment characterized by a mixture of loose sand, clay, and water. They're highly saturated with bitumen, an organic hydrocarbon that is key in forming petroleum. Not only does the LA basin have rich oil sands, the layers of oil sand are thick AF. We're talking thousands of feet thick. To cap this first point, we've got thousands of feet of highly saturated oil sands. Speaking of capping, which I'm not right now, we also need caps of non-porous sedimentary rocks to trap the oil and natural gas. That's where our second key ingredient in LA's oil comes in: anticlines. In structural geology, an anticline is a roughly A-shaped layer of sedimentary rock that is formed by compressive tectonic forces. They're quite particular in the conditions in which they form. Squeeze the land too little and you don't get anticlines. Squeeze the land too much and you break them, or even worse, regionally metamorphose them. It turns out that the tectonic regime that we just discussed is perfect for the formation of anticlines in the Los Angeles basin, and luckily for us, the anticlines that formed here are not porous at all and do a great job acting as reservoirs for oil and natural gas. Exhibit A of what happens to oil and natural gas without anticlines is the La Brea tar pits. Oil and natural gas wants to escape up and out of the earth, as it is light and buoyant, but anticlines are so important to the extraction and deposition of hydrocarbons because they allow them to pool and inhibit escape. At the La Brea tar pits, an active fault by the name of the San Vicente Fault cuts an oil-rich sedimentary layer from the Salt Lake oil field, allowing the oil to flow up the fault and pool at the surface of the earth, releasing natural gas such as methane as it does so. As the oil surfaces, the petroleum biodegrades and/or evaporates, transforming the crude oil into asphalt, rendering it useless for human extraction and dangerous for curious Ice Age creatures. Despite their extractive impotence, the La Brea tar pits are an absolute geologic wonder that have facilitated the necessary conditions to contribute a priceless amount of knowledge to the sciences, especially in biology and geology. I highly recommend visiting them if you haven't already. Their museum is awesome, and the amount and quality of Ice Age fossils extracted from the tar pits is astounding. The Los Angeles basin is insanely well endowed in oil and natural gas. It contains over 40 active oil fields with 4,000 currently operating oil wells. Oil was first discovered here in 1892, and Los Angeles has been pumping it out since then, producing as much as 1 billion barrels of oil per year in the late 1970s. In 2024, Los Angeles County produced 622,000 barrels of oil, a far lower number than those of the late 1970s. This is largely due to the vast majority of the area's oil wells drying up, but the greater shift to renewable energy is also a factor in the decline of oil production. One specific area of Los Angeles where oil is still being actively extracted is the Baldwin Hills, just east of Santa Monica and south of Hollywood. The Baldwin Hills are a textbook example of an anticlinal dome, hence their productivity in oil. Los Angeles is, in my opinion at least, a strikingly beautiful city with some of the most interesting geology in not only the country, but in the entire world. While it's famous for Hollywood and air pollution, I think more people should know about its awesome geology. The complex geology of Los Angeles alludes to an eventful geologic history, an unstable geologic future with many faults, pun intended, and some of the world's richest oil deposits. Hopefully you learned a thing or two in this installment of Solomon's Outdoor Adventures and enjoyed doing so. If you haven't already, please consider liking and commenting on the video as well as subscribing to my channel, as it really helps me to get more content like this out to y'all. Thanks for watching, and as always, peace! Thank you for tuning in to another episode of Solomon's Outdoor Adventures. If you enjoy content like this, please like the video and subscribe to the channel, and check out some of our other adventures right here. As always guys, thanks again and peace!